last minute to this to teach today's course. I was asked by Professor Karac. I'm not sure, Sandy, if do we need to do anything before we start, or? Okay, I guess I was able to share my screen. So. Can someone confirm that you can hear me and I'm not just talking to the air?
Yes, we can hear you.
Excellent, thank you. Okay. So apparently the organizers have left. So that must mean that there isn't something official like that we should do. So I'm not sure if you have any, if you don't have any objections, we are going to start. I'm going to do some explaining for 3 hours. Feel free to make me stop at any time. I mean, stop me at any time if you think, if you have any doubts, or if you have any questions, or if you want to point out a mistake that I have made, or something, or just want to raise an interesting point or comment. If you don't understand something. Okay. Can you confirm that you can see my screen, and on my screen you can see a large terminal showing a Jupyter notebook?
Yes.
Excellent. Can you read the letters? Because that's important.
Yes, we can, but I think it could be a little bit larger.
Okay, let's see something like this.
Perfect, thanks.
Excellent, thank you. Okay, so today, this is the second lecture, as I understand, the supervised and unsupervised learning. So where we are at this point is András was talking about, Professor Horvath was talking about on Monday on some basic introduction to PyTorch and stuff, and how to do classification. So I'm going to build a little bit on top of that. And where you're going to do, what you're going to do tomorrow is Professor Karac is going to, if I remember correctly, he's going to show you Gaussian mixture models. So that's going to be at the unsupervised part, but we are still at the supervised stage yet. So today I have posted in the chat two things. First one is the class 2, the skeleton Jupyter notebook that I have also opened here, so that we can fill it together. It has a lot of to-dos that we need to fill out, and in the end, we hopefully are going to learn, see some interesting things and learn new stuff. And the other thing that I've put on the website, sorry, it's going to be up on the WIC website. It's just so last minute that I just put it on my website here at the university. So it's just a temporary location, but if you can't access it for some reason, or you can't find it, then let me know and then we'll sort it out. So the second thing is the so-called dataset.npz file. Now I understand that last time you downloaded, you were working with the either synthetic datasets or the MNIST dataset, and the MNIST dataset is conveniently included in PyTorch. Or precisely, it's PyTorch includes some utilities for downloading the MNIST dataset, But now we're going to work with some synthetic data set that I cooked up, which you can open here. So first point of order, let us import some stuff. As you can see, we're going to be working with NumPy. We are going to visualize with Matplotlib, and we are going to do machine learning tasks from. Oh, sorry. Let me rephrase that. We actually don't. I actually don't need the %matplotlib here. So let me restart the split here. Yes. Okay. And we are going to use Torch to do the actual machine learning, make the machine actually learn. So I'm not sure if you have talked about. I saw that there was a course where you learn some NumPy and scientific investigations. But one of the easiest ways to just save data sets is to use the NumPy save and load feature. So that's what I did. If you load this dataset file will not be found because it's not here on my computer. If you're using Google Colab, you need to upload the file that I have. Well, I'm showing on your monitor, on my monitor, but you can't see that. So here, the file that I've uploaded on the website. Here, I think it's at the /tmp folder for me. But you need to point it wherever you upload it to Google, or if you're doing this locally, then wherever you've downloaded it. So now you can see that this is a simple data set with 500 data points and 2 features. 2 features is really convenient, as we can see, because we can simply visualize it. I am telling you a secret that this is exactly the reason why it's 2-dimensional, so you can have nice visualization throughout this today's class. So let's do some visualizations. I'm not going to need my touchpad here. So let's say I don't really like the PLT notation. And then let us visualize what we have as input space. So it's not a great secret that if you print this out, this is 2 columns. The x, the x is the one. So the input is called x. X has 2 columns, in the first column, the second column, and the 1 and the 2 second features of this data set. So we can visualize them in space, something like this. Okay, so this is basically how our data set looks like. It's a nice display thing. This doesn't tell you, doesn't really tell you much. So what I'm going to do is visualize the positive and the negative classes together, so that positive, let's call it positive mask. Let's filter for y being equals 1. Let's see what y contains. So it contains 0s and 1s. It's going to be the negative and the positive class. And what I want to do is simply plot the positive class here. Let's say, and let us denote this by positive, and the negative, which is not positive, and let us call this negative, and let us show this in our plot. Oh wow, okay. Positive mask, okay, this should be a 1-dimensional mask. Okay, so now we can see that we have a nice data set. And what you can immediately see, this is your training data set, by the way, so we are allowed to look at it. What you can immediately see that there is a sort of, so there are 2 classes. One is within each other. If you've talked about this before, then this class is, this data set is not linearly separable. And it's more or less, the two classes are more or less distinct, but this has heavy noise inside it. So I added I think I added a 0.2, a Gaussian additive noise with a 0.2 standard deviance. So that's why the two classes are sort of bleeding into each other. So this is what we are going to try to classify today. And we're going to go through the motions, and then we'll see what comes out. Okay, so that's out of the way. Let us define a simple model. If I understand correctly, but feel free to stop me. You have defined simple PyTorch models like this, right? Actually, at this point, I think it now would be the good time to for me to pause and then wait for a couple of seconds to let you ask questions if there are any. Okay, probably no questions. That means either everyone is busy trying to load the data sets, or everyone is busy sleeping, or everyone understands everything and is just waiting for the others to ask questions. Feel free to interrupt me while I'm talking, so it's not like I can hear you, hopefully. So I'm a sort of adaptive video. So let us try first, why not, 2 layers. It's going to be a linear network. I can also visualize this so that we have the input X, and it's going to go to a linear layer, which is going to be 10 wide. These are going to be, if you have seen this older notation where you have 10 neurons and your X, well, you have X1 and X2, and then everything goes into everything. This is a sort of very cluttered notation. And then afterwards, it's going to go towards that one output. But I prefer this layerized notation because it's much more compact. So you will have a linear layer, and then we are going to have a ReLU nonlinearity, and then we are going to have another linear layer, because we are going to have, so this is 10, this we are going to have an output Y, which is either positive or negative. So it's sort of a number that's going to be, if it's positive, if the number is positive, then it's going to be a positive class, and some number is negative, and it's going to be the negative negative class. Yep. The one thing I'm not sure you have talked about, but I am going to mention briefly, is this ReLU or ReLU, or I'm not sure what it's called, how it's pronounced actually, the rectified linear unit. So what we have here is, if you, again, I'm not sure if you think about it, that linear layer is simply just a multiplication and an addition. And chaining multiple multiplications together is basically just one big multiplication. Well, theoretically anyways. So what we want to do, if we have multiple layers, we're going to compose them. We want to separate the linear layers. It's actually another linear layer with nonlinearities. And the specific nonlinearity that we have here, this is the so-called ReLU, is, let me annotate this diagram. This is the input, and this is going to be the output. So the ReLU is going to be the maximum of 0 and x, where x is the input. Okay, so this is basically the nonlinear. It's mostly linear, but there is one small sort of breakpoint, so to speak, here at the origin. And actually, we're going to use a slight modification of it, which is the so-called leaky ReLU, so-called because it's leaking here. This is the leaky ReLU. Forgot how to write. So this is actually the maximum of minus alpha. So it's going to have some alpha times x here, and then x when x is positive, where alpha is something like 0.1, I think is usually the default. So it's not actually horizontal in this region. It has the same breakpoint or breaking point or whatever here, but it also has meaningful values here. It's a bit more efficient because it's a bit more performant because you have because neural networks are trained via gradients, and the gradient of this ReLU is 0 at this point. So it basically consumes some information, loses some information that we need. Okay, so let us define this model, and actually layers are more or less defined for us. What is missing is the linear, the non-linearity. So what we want to do is simply to call these layers for x, and then I want to call the leaky ReLU. I'm not sure why my code completion has died on me, but I sort of remember what to write. And then another layer, FC2, and then notice that there is no output nonlinearity here, and that's because at the end, when we define our loss function, the actual loss function in PyTorch, the binary cross entropy that we're going to use, is defined in a way so that it actually uses the logits. So these are the logits that come out from this model. And not the actual, I don't know, true, false, or positive, negative, or 0, 1 output. So it needs to use these logits. Okay, so I mean, let us run this model. Okay, well, yeah, I have run this model. It doesn't do anything. It just declares the model. Let us do some training routines after we have defined our model. So first we have the train on epoch, which is that the epoch is one pass through the database. Sorry if I'm, I don't know, mentioning some stuff that you already know and you've already discussed, but I sort of just substitute, so I don't quite know what you have covered already. Feel free again to ask if there are some questions. So one epoch is one pass through the database, and the convenient thing in PyTorch is this so-called data loader. So data loader is something that you can iterate through in train data loader. And this is going to be the x and y's of our of the actual training data set. Okay, so first, what we want to do is to zero out the gradients, the gradient buffer, so that we can do some calculations afterwards. And then I am going to oh wow, okay, this is going to be some interesting folding here. I'm going to so let us run the model. The model let us run on X, the inputs, and these are going to be the output logits. And then afterwards, what I want to do is to train the loss. Calculate the loss, which is nn.functional dot, and I'm going to use binary cross entropy with logits. And we are doing binary cross entropy because we have a binary output, because we have a binary classification problem. And we are going to do with logits because it's more efficient and more numerically stable, has less errors than if I did the other one without logit. And this leads, let me see the input. The input is going to be the predicted logits. And the output is going to be, the target is going to be the y, so the actual ground truth variables. Okay, and then I'm going to need the loss.backward. So that's going to calculate the actual gradients, that's this line here, and then optimizer.step. Optimizer is going to contain, so it already contains, well, we don't have documentation at this point, but optimizer is going to contain the model parameters, and this step is going to take the model parameters, calculate and take the gradients that have already been calculated in the backward step, and then take one step into the negative gradient direction, basically do the gradient descent step. Okay, and another thing I'm going to need to, I want to have train loss. I want to keep track of the loss as the training progresses. So what I want to do is here is simply gloss, well, it's just going to be one number. This is going to be the loss for this batch, and then this and we are going to multiply it by the batch size, which is going to be the shape of, the first shape, the first value of the shape of X, the number of rows, basically. That's going to be your batch size. And then at the end, let us return the train loss divided by the length of the whole data set. Let us format the code a little bit. Okay. And then this is going to be training on one epoch only. And then afterwards, we want to train multiple epochs because it's an iterative algorithm. You see that I've already prepared the losses variable here, so I'm going to collect the losses for each epoch. So let us iterate over the number of epochs. And then we need to call the train epoch. So what does train epoch need? It needs the model. Well, the model is here. It's going to need an optimizer, where I'm going to need an optimizer here. And a train data loader, I'm going to need a train data loader here. So let us define an optimizer, which is the torch optim module. If you see here, I loaded it from the torch library. The torch optim module contains lots of optimizers. I'm going to use a simple SGD here for now. And this needs the model parameters, and the learning rate. Okay. And optimizer is defined now in, the training data loader. And this is going to be defined. So Torch has these very handy data loaders. I think I've seen you using them in the previous code, but I'm going to show it again. Utils data loader. Yes, here it is. So this is going to need a data set, and conveniently we have the training data set here. This is going to need, well, it's not going to need, but we're going to supply a couple of other options. One is that I want this to be shuffled. What this does is basically, well, shuffles the data set. Every time I go through an epoch, it is going to go through in a different order. And if I am doing mini batches, which I am, basically, I'm going to go through the data set in small chunks one at a time, meanwhile updating the model parameters. And that means that if there were, if there was any sort of bad or negative pattern or influence in the data set, that's going to be shuffled away. So basically, the samples are going to become sort of independent. And the mini batch, so the algorithm is going to encounter different mini batches every time, every epoch. And then let's say the batch size is going to be, I think I've already defined, yes. This is going to be the batch size, 32. I just picked a random number. It's not going to really matter at this point because, and again, you notice that I didn't do any sort of move it to GPU, move it back, etc. And one reason for that is because I'm too lazy to run it in a collab or a remote environment, and my laptop does not have GPU at the moment. And the other reason is that it has only 500 data points, and the model has, I don't know, times at most 100 parameters. So it's not really worth shuttling the parameters back and forth and the data set back and forth, the GPU and the CPU. It's not going to be that much of an improvement in speed. So I'm going to train on CPU now for these synthetic data sets. Okay, so we have the train data loader. And yes, and the train epoch is going to give us back the loss. So we say that losses dot append train epoch, or we can more easily say, more prettily say that the loss equals train epoch and the losses dot append loss, and it's going to return the losses. Excellent. Excellent, excellent. Okay, so one thing I'm going to change here is that I want to, this is going to more or less work, but I want to have a nice progress bar of how the train is progressing, because I don't like that. I don't really like that it's doing nothing and outputs nothing. And progress bars are always fancy. So I have imported here Takadum. This is the library is called Takadum. This is a really cool library. You should check it out if you haven't already. This is going to give nice progress bars, and you can just, so this was a range before, and you can exchange it to T range here, and it works all the same. It doesn't matter. Okay, I think the training model is done. Sorry, that the training of the model is done. And now there is an accuracy, and I think, yeah, it actually, so I forgot to change this. Never mind. I'm going to redo this bit. This was supposed to be removed from the skeleton data set that I provided, but never mind. I want to calculate how accurate my model is. So I go through again. I go through the whole data set. So actually, I can simply copy this code here. I will need the same data loader. Well, it's not going to be trained data loader because it's going to get any sort of data set. It's going to load the data set, and I don't need shuffling at this point because I'm not going to train. I just want to go through the whole data set one at a time. I have one mini batch at a time. And then another thing that's different is that I don't want to calculate any gradients. So I will call torch nograd, which is going to speed up any sort of subsequent calculations because it tells torch that, no, you don't need to keep track of the gradients. It's fine, believe me. And then I'm going to define the same loop as before in data loader, and y predicted logits is the model x applied to x. I don't need an optimizer. I don't need zero grad anything. That was for training. And then I'm going to, so these are the logits. What I want to have is the output of the model. The final output is either positive or negative. Okay, so let's say this dy predicted is going to be y predicted logits larger than 0. Okay, so this is going to be a true-false output. Basically, it's going to tell you whether it's a positive or a negative class. Okay, and let's say we have a count, let's say correct, and the count correct is going to be increased by whether how many samples or how many outputs are correct, in that how many predicted outputs are the same as the y, which is converted to Boolean at this point. And this is going to be converted to torches in so that it can be added to this number. Yep. And we are going to return the count correct dot item. Okay. So this is going to be our accuracy. This is going to tell you on a scale from 0 to 1 how accurate your model are, how much of your samples are agree with the prescribed outputs. I'm going to leave this up, and I'm going to ask you if you have any questions. Because if not, I need to take a couple of minutes break just to let you simmer on it, and I'll be right back. Terribly sorry about that. I'm back. Can you confirm that you can still hear me? My headphones are going wonky when I take them
Yes,
off
okay.
my head. Excellent, thank you. Okay, so and were there any questions during this short intermission, or has someone come up with a question? Okay, no questions yet. Excellent. Never mind, and no matter. We're going to go towards actually running this code. So what we have here are two data sets, X and Y. But what we are going to need are PyTorch tensor data sets. So let us create a training data set from them, which we can do easily convert from Python to Torch using the tensor .tensor dataset, where we simply enumerate all the tensors that we need to use, and we need to convert them from NumPy. So I want to have the X as my first tensor and the Y as my second tensor, because you see here that we extracted the X and Y from the tensor. So this is basically what determines the order of the two tensors that you get from the minimatch. And actually, because this is just a minor detail, but NumPy by default uses oh, it's already in 32 point. Never mind then. Because I was about to say that NumPy by default uses 64-bit floating point numbers, but PyTorch prefers 32-bit floating point numbers. So what I usually do is simply convert them to convert the arrays to 32-bit floating points, so single precision numbers. But as far as I can see, so X data type. Oh no, sorry, that's going to be 62. So never mind. We are going to need this. Yeah. So we're going to convert both arrays into 32-bit floating points, and then create PyTorch tensors from this. So if we run this, we can see that this is going to be this is going to be a data set, and if I remember correctly, you can get the tensors from it. So this is going to be your first tensor, 500 lines long, and this is going to be your second tensor, which is going to be the Y. And if you see here, well, the D type, not the D type, the 0 D type is going to be float 32. Actually, the output D type doesn't really matter, so I can leave that as is. Okay. Okay, so let us use everything we have defined, and we have a simple model with the number of input features, which is going to be, I think, 2, as in the 2-dimensional space. And then we are going to train our model, let's say, for 1000 epochs, and then we will print out the accuracy. Let's see if everything is working. Something is not working, because I think I haven't run this cell. Okay, so something is doing something. Okay, result type float can be tossed. Sorry, no, something went wrong. So we have as outputs single precision floats, which is as expected. We have as ground truths the Y's as int 32s, and apparently binary cross entropy, let's say it might need to have it also as floats. So let us again convert this into floats. Okay, this works now. So what I don't quite like in PyTorch is that it is sort of picky about what data types it needs for its different operations. So it chooses the data types and it doesn't like to mix and match, which on the one hand is sort of understandable. On the other hand, it's quite a pain if I want to multiply two precisions with each other. So let's say a single precision with a double precision. Something has gone wrong. Let's see why. And it's interesting because when I prepared for this class, the training was much faster. Okay, now I made a mistake in trying to debug the wrong thing. But because I have Teams running on in the background, it's using so much memory, so much CPU. Yes, it's using, I don't know, at least half of my CPUs to just encode the video and then maintain the code, so that my training became much slower. Okay, so with the accuracy, so the y is going to be model x, model y, predicted logic, etc. It doesn't really change shape. So let's put an assertion here that the predicted from shape equals the y.shape. And then run this again. This time only for one epoch, so that the error comes out much faster. Okay, y predicted from shape, y.shape, yes, y predicted equals y.toTorch.bool. Okay, that's something. Okay, we can see that there are some correct and incorrect samples as well. Oh yeah, I forgot to. Oh, okay. I forgot one very important thing is that I actually don't need to cast this into integers. What I want to do is count the non-zero elements, because we have this tensor. This is going to be the Boolean tensor of whether the samples are correct. I mean, the outputs are correct or not. And we want to count the two elements from this. Okay. And actually, we can just say item here, and then I don't need. Yep. Let's format this code. And then run one. Oh, okay. Something is wrong because the model accuracy, we are not returning the accuracy, we are returning the correctly classified samples. We need to divide this by the length of the data set. And that's going to be 52, which is par for the course, as I didn't really do any training. And there are approximately, I think 50 positive and 50 negative classes oh, sorry, 250 positive and 250 negative classes. There's negative samples, positive and negative samples in the data set. Okay, so let's do the training for real. I'm going to wait for 30 seconds for you to ask any questions, comments that you might need, that you might want answered or want to tell.
Sorry, Professor. Will you be able to share the Python code with us at the end of the lecture?
Yep, I plan to.
Okay, thank you.
No worries, no worries. I think there is also the recording of this class, so if you If you look it back and you miss something, then you can look it back. Okay, so 85%. That's not bad. That's not too bad. Not too bad. Okay. So let's see how this whole thing. Let's see first if we converge to something, or if we need to train this a little bit further. So let's again open a new plot, and then simply plot the loss. And then this is going to be the epoch, and then the y label is going to be the loss here. Okay, so as you can see, it more or less converged. It actually converged, I don't know, after 200 iterations, so the loss didn't really decrease anymore. It's very interesting. We're very high loss. Have I forgot to divide, normalize? No, I actually normalized it. Huh. Okay, let me check something real quick. So this is the binary cross entropy. And what I'm checking is whether the return loss is actually a sum of the losses for the data points or a mean of them. Reduce the reduction. Okay, string option specifies the reduction to apply the output. No reduction with the applied mean. Yes, some yes. Node size to default mean. So it's the default. Because if I take the mean, so this is the mean loss, and which is good actually, and then I multiply it by the shape, so the batch size. That's going to be the sum of the loss. And if I sum those all up, then then divide it by the length of the training data set, then that's going to be, okay. Never mind. At this point, what I would like to try is that the length of the data loader might not actually be the length of the data set, but rather than. So this is going to be, let's say we change the API a little bit. This is going to be the sum of the losses for the whole data set. And then here, I'm going to divide it by the length of the trained data set. Oh, sorry. And then I'm going to just do 200 iterations because it's perfectly enough. And then let's plot this again. You can see here that the actual losses, so actual accuracy it's a bit less. So we could train it further, and then it might be more, or it might just be some stochasticity, some randomness. In that we have randomly initialized the model parameters, and then after every run, the result will be a little bit different. But now the loss values are much more sensible. So this should be ideally, because it's sort of an easily separable data set. At least it doesn't have really, so there are some ugly data sets where the loss is going to be in the hundreds or in the tens as it was before, but it should be below 1 in any case. So in this case, so I think this was the problem. Okay, and but this actually only tells us what sort of how the model has converged. So if it converged or not. What we want to do is to look at the model, the actual model, and I have drawn up a little bit of script here. I didn't sort of put it as a task here because I think you have already done visualization, so it's not out of scope for this lecture. But what this does is basically takes your model, the input and output data sets, and going to visualize it is at a certain resolution. The resolution is needed because it doesn't matter. I'm using a contour somewhere here. Yes, a contour plot to visualize the decision boundary. So if I run this, yes, and I want to visualize the model. So this is how my model looks like. So this is my, these are the yellows are the positive, yes, the positive class, and the blue is the negative class, and this solid blue line, or might be purple, I'm not sure. I think it's dark blue. Line represents the decision boundary. So everything inside, that's going to be the negative class, and everything outside is going to be the positive class, which you can't actually see from this plot, but when we look at the accuracy, it's not that terrible. So I think it's going to be the correct, correct way. It's not inside out. But you can see that there are some certain points that it can still not really classify that well. I mean, it could have gone something like this, so that there are more data points here, the more blue points, and somewhere here may have been better. Let us try to do something a little bit better. Let us try to do something more. Okay, and this is going to be an aside. So this is going to be a sort of sidetrack. This is not overfitting, not validation, and not regularization. Well, sort of regularization. But I think this is important at this point to introduce the concept called feature engineering. So far, what we have done is simply take our inputs and then run the whole model onto it end to end. This is, well, the usual way to start with deep learning. This wasn't always the case when we had linear models. Well, I say we, but it was before my time as well, not at all. What the usual method is to, in addition to the X, Y, and X2, we had all sorts of features, F1, F2, F3, F4, etc., handcrafted to tell the model what to look for. And basically, the model needed to simply weight these features all together. Nowadays, with deep learning, is not that it's not that important, but feature engineering, like for example, think about it. Nowadays, what you did with the MNIST dataset is that you put the whole image into the model, like you would with the trash and the that machine that's basically chomps down trash and compresses it, and out comes the output, out comes the decision. What they used to do is to look at key points like edges and corners in the image, and then from those try to make up eyes. And well, in the digit classification, you don't actually want to have eyes, but horizontal lines everywhere. And based on that, the model could output some decision. But sometimes feature engineering is useful. The only example that comes to mind is when I was looking at chess engines, and they not only included the board, but they included the specifically categorized pieces of the chess and some other hints. If I remember correctly, some potential moves as well were inputted to the model, so that it doesn't need to calculate it for itself. So everything that the model that is hard to calculate for a model. Remember, the model is basically matrix multiplication and some really basic nonlinearity. So everything that the model presumably cannot calculate, but presumably is useful, that can be included as new features. So if we look at this output, which I've already closed it, we can see that it's something like an ellipse. So we can help the model by inputting elliptical features and say that, well, not elliptical, sort of polynomial features. So we can multiply together some of the input parameters, and then we can let the model make use of them as well. So for two inputs, we have three possible outputs. So actually, I'm going to leave this and start with this one first. So I'm going to define a new x, which is going to be the a stack along the first dimension. Remember, the 0th dimension is the batch dimension. The first dimension is the feature dimension. And I'm going to define new features, which are going to be the x1, x2, x1 times 2, x1 squared, x1 times x2, and x2 squared. And we have 1, 2, 3, 4, 5 of these. In general, we're going to have non-polynomial features is the in features times in features plus 1 over 2 plus in features for the linear features. This is for the second order features that make up our sort of ellipsoids shape. Okay, and then afterwards it's as it was before. So x equals self.fc1 x equals nn dot leaky relu. Oh, sorry, functional. Say function. Thank you. Leaky relu x equals self fc2 x, and that's it. Okay, it has a little bit more parameters because the first linear layer is going to be connected to more input, but otherwise its complexity or its power comes from the fact that we have handcrafted some features that we want to use. And you can always do that as long as you know something about the domain that you're working on. So for example, if you're an informatics student and you were just given this task, okay, this is your data set, and then produce some output, then it's not going to work. But if you're a domain expert, like a physicist or a geographist or a meteorologist or a psychologist, I don't know, you can come up with interesting combinations of the input data that might help your model. This is more of a data science topic, by the way, so it's not really machine learning. Okay, and let's fit it again. So this time we are calling it polyfit. And if you look here, this is the nice progress bar that I was talking about. And at 0 cost, it's going to give me. I'm going to bring the model itself back on the screen. So this progress bar at 0 cost is going to give you an estimation of how much time it's going to need, or how long does your training take? How long your training takes? Are there any questions, by the way, up until this point, or everyone is more or less with me? No questions yet. Okay, so let's visualize this, what we had before. So what you can see here is that it's a bit more complex model. May not be immediately apparent, but if I zoom in a little bit, so there are some nonlinear. So before it was 10 or 11, I don't remember, so it was a broken line made of 10 or 11 segments. So a simple 2-layer ReLU MLP is only capable of broken lines of that amount. But this has non-linear features as well. So the features themselves, the inputs are non-linear. You can think of it as you have a highly specialized non-linear layer in the beginning. So your broken lines will become a little bit more curvy, and that can help. In this case, it did not help that much. I mean, numerically, there were some edges that started to appear, but well, as a data scientist, I would say that these are just artifacts. This is what we're going to actually look at. So how much this data, so how much, I don't know, little, zigzags are actually warranted in this case. But this was just an aside because actually you don't have, so we usually don't have this kind of, we don't really have this kind of, I don't know, domain knowledge, or sometimes we don't have it. We just have the data and run with it. So let us define a larger model, a really large model, like it has went to the gym and then became really, powerful. I'm going to introduce something called sequential because it's going to make my life easier. I'm just going to throw layers at it. Let's say we have, no, that's not self, and dot linear in features, and let's say 128, and then leaky ReLU, and then linear 128, let's say 64, and another leaky ReLU, and then another layer. Let's say it's going to go to 32. It's a 3-layer, or sorry, 3 hidden layer neural network. Leaky ReLU. And the final linear layer to damp it all down to 1, because we're going to need 1 output only. Excellent. Okay, so we basically do in the forward step. So how do we execute this? Is simply just self.layers. So self.layers is a sequential layer, and what sequential does is it's going to compose each layers one by one. I'm going to go through each layer one by one. So this is going to be your larger model. And I'm going to train it a little bit more as well. More time for you to have questions. Well, 2.5 minutes. Again, this was a little bit faster when I did this exercise in the afternoon on my laptop without Teams running. And let's see what this is going to produce. Meanwhile, if you have any questions, then feel free. Wow, it's starting to slow down. Or me fiddling with Teams is what's slowing it down. well, the potential disadvantage of having a progress bar is that it can be highly addictive. It's sort of, especially if you write out the, if you have some sort of a dashboard of your loss function, so that the, so that it's always plotting the, excuse me, your losses, and then you can say that, oh, it goes down, oh no, it goes up. It's like, you know, when stock traders are looking at the dashboard, and then trying to, or when you're looking at your favorite teams matches and stuff. Okay. And of course, the bad thing is at the end, okay, well, nice, we have some sort of accuracy. And I was going to say that disappointment, the disappointment at the end is when it all goes away with a small mistake and goes into runtime error. Okay, let's try to visualize the loss again. It was somewhere here. Yes, well, it could have gone further, but let's stop here because we have a limited amount of time. And what I want here is to visualize again what it looked like. And what it looked like is this. So as you can see, the 93 accuracy was achieved by having a really weird shape in that it has holes in it. Like it wants to correctly predict these samples, which are, I would assume they're sort of noisy and they're outliers. And this region here, which I think is, I don't know, it's sort of trying to classify these three correctly, but it has so far failed to do, but it's in the process of doing so. And it has some sort of nice base here. So, yeah, it comes out here with a sort of tentacle and then tries to grab these two. Is that positive now? The negative samples and so forth. And again, here it tries to do all these 4 or 5 positive samples. So it's highly nonlinear. It looks ugly as hell, but it's 93% accuracy. So we are happy. Well, or are we? Now the thing is, let us backtrack a little bit. So so far, I'm not sure if you have done this, but this is a sort of, I'm not sure if anyone has shown you a figure like this. But usually what we do in machine learning, the process is that you have a data set. This is called a data set, and usually I denote it with the capital calligraphic D. And from the data set, you will have X and Y points, inputs and outputs. In case of supervised learning, in case of unsupervised learning, you're going to only have X point or something like that. And then you will have a model class. From which you're going to a model class like, I don't know, neural networks, random forests, XGBoosts, linear models, Bayesian networks, etc. And from this, you have your training algorithm. We have used SGD here as an example. And your algorithm is going to select the minimum from something, one of the models, which will minimize the loss given on the training data set. And this was what we have been doing so far. So we were given a data set, or I gave you a data set. I gave us a data set. I specifically crafted for this example. We had the model class. We had actually several model classes. We can have several model classes as well. Class 2, for example, like you have 2 models and you want to sort of choose between which one is better, etc. And you have another data set. So this was your training data set. And you have also the test data set. And you will have some sort of evaluation. Let's say you're going to use the accuracy on your test data set. And notice that you do not, this is going to be your train algorithm. So this blue is the training pipeline. And this green stuff is your evaluation pipeline. So here, this test data set should be separate from the training data set. It's sort of like a third party, it's not third party, but impartial view, like an independent review of how well your model actually does. And this is going to be sort of a proxy of how your model is going to, because in the end, you want to train a model not only for the joy of putting yourself up on the leaderboard or something, or a Kaggle leaderboard, but to have a model introduction where it can do useful stuff. And this test data set and the evaluation on it will help you understand how well your model is going to perform out in the wild. So what we are going to do is that this data set also contains an X test and the Y test data sets or arrays. I think these are the only things in this data set, so no hidden surprises there anymore. I am going to, well, I've loaded it here, and I'm going to define a test data set, which is going to be torch utils data tensor data set, and again, torch from NumPy X test. And Y test. Okay. And then we have the test data set. Again, the X test it's only just 100 data points. Again, 2 input features, like it was before. And this is sometimes smaller than the training data set. This is sometimes more than the training data set if you want to have really precise measurements. You can think of it as, you have done your training, you have run your model, and then your boss came in and then supplied more data set. I don't know, this just came in from the customers. Try it on this. So you can have more data as well. Any questions, by the way, up until now? I have a notification in Teams. I'm not sure if it's related to the, no, it's not related to this call, okay. If there are no questions, we have the tensor data set, the test data set. Let us print the accuracy. Opa. Okay. So we had a really good 93% model accuracy on the training data set, but we had a 77% accuracy, test accuracy. So something is off. Okay. Let us visualize what's going on in the test data set, which is what usually we don't do, because we don't use the test data set for anything than the final evaluation. Otherwise, it's going to become just another part of the training data set. But in this case, for pedagogical reasons, I'm going to show you some stuff. So what we can see here is that, these holes, which were exactly for the reason to accommodate some of the positive classes. Well, it's full of negative class examples in them. Well, except for here. And this here is also unnecessary. So basically, yes, the training data set was noisy. And because of the noise, we needed to have this weird shape, but the test data set and the data set out in the wild is going to be noisy in a different way. So what we want to do is to have a sort of more general shape that works equally good on the training data set and the test data set. So if you go back, well, actually, we don't need to go back. So these are intuitively, these holes are not really necessary. These are so-called, these are so-called overfitting artifacts. So the model thought that actually these are symptoms that the model is taking the training data set too seriously. What I mean by that is that it thinks that its only job, well, that's how the algorithm works. It thinks that the only thing in the world, the only goal it has is to optimize the training error. Whereas it's not the training error we actually optimize for, it's the test error, more precisely, the error that you're going to have out in the wild, the so-called out-of-sample error, which you don't really have access to. And the test data set is sort of just a proxy for that, so that you can measure on something that's sort of independent from your training data set and training process. So this is a discrepancy. And with a more powerful model, it's more even, so it becomes more visible, because a more powerful model can optimize and fit to your training data set in certain ways that is not going to generalize well. And I have printed it out here, the test and training accuracy for each model. And you can see for it, this large model, this is the highest train and test accuracy. Sorry, this is the difference between them. So we have, I don't know, over 10% in accuracy. This difference between the train and test accuracy is what's called the generalization gap. Because what you want is to have a model that generalizes well to unseen data. This is where machine learning basically stops being just curve fitting and starts to become something a little bit, has to take more into consideration. If you go into learning theory classes, you are going to see curves like this. So this is your, error measure, which is going to be the opposite of accuracy, but bear with me for a moment. And let's say we start as the capacity, the horizontal axis is the capacity of the model. So this is your more powerful algorithm, more powerful model, etc. And for the same amount of data, what you will have is that the training error is going to start from somewhere high, because if you have a low model, then it cannot really learn anything. So the error is going to get high. And then as you progress, the model is going to go down, basically. And you also have the error test, so to speak, or the out-of-sample error, which is also starts from high, and then it's going to go back up. And this is, so we can say that this is the underfitting regime, where you don't really, your model is not powerful enough to do the task that you want it to do, to solve the task to want it to. It's too weak. And then you have the overfitting regime, where your model is too powerful and it does not know that it's too powerful. So it will try to exploit some things that you don't want, like the holes in the picture. Like like, I don't know, realizing a really weird shape just so that it can maximize its accuracy. It's like, you know, those students who really study for the exam and learn everything by heart, all the theorems, all the proofs, etc., but then can't solve a single task outside in the industry. It's something like that, not quite, but something similar. So this is going to be the overfitting regime. And what we want is this sweet spot when the, well, we don't actually care about whether the generalization is good or bad, but it would be nice if it was good, if it was really small, because then we would have some concrete measure in our hands. But we want is to have the minimum out of sample of test error. And this is the model that we want. This is the, I don't know, star, red point, or bonus points, or I don't know. This is used to be the classical view of things. Nowadays, with deep learning, it turns out that it's funnily enough, there is a sort of double descent here. And as far as I know, no one knows why, really. But empirically, they have shown that this is going to be the this is the so-called double descent regime, where the tester again starts to go down as the models. Because if you, for example, if you think about the ChatGPT, I'm not sure if I think everyone has heard about ChatGPT, and like they're a couple of billion parameters, and they're really huge models, and they generalize well, so they work outside of their training data set. So modern deep learning is sort of a weird animal in this regard, that it has it doesn't really hurt to overfit, but it's simpler models like these ones that we have defined, and actually synthetic toy data sets, it's much easier to just get stuck in the overfitting regime. So you need to take this into account when you do your machine learning implementations or tasks. Any questions about this or any comments about these? Okay, no questions yet. We can also comment on the chat. I'm regularly checking it. I hope I get some notification, by the way. If you don't want to, I don't know, unmute your microphone or anything. So what can we do? Well, we have seen that with simpler models, it's harder to overfit. Also, you can run into the underfitting regime, so you have to. It's sort of a trade-off. The rule of thumb was that you needed 10 times more parameters. 10 times more data than the number of parameters your model has. So for example, here we have, let's say, 500 data points in your training data set. And we have, in the simple model case, let's see, we have simple model.parameters. We have 41 parameters in the simple model case, and we have 10,753 in the large model case. And we only have 500 data points. So basically what the large model is capable of, it's capable of memorizing its entire training data set and then just simply regurgitating that. It can do that. We can also well, regularized, we can also guide it towards solutions that we think are best, and that's what regularization is. So one thing that we have observed is to have smaller models. But what if we want to have larger models? Then we have some tricks we can do to make it more robust and make it generalize well. One idea is to insert some noise into the data set. This is an area, loosely, an area called data augmentation, where you basically artificially enrich your data set. So instead of 500 elements, you will have, I don't know, a couple of thousands, or 100,000 even, or because you can have all sorts of noise injected into it. For example, in this picture, if we have, well, I'm going to show one of the figures that well, not this figure. I want to, yes, have this figure. If you have, for example, if you inject random noise into the data set, what you will have is these points are going to multiply here. And then at the end, you're going to have, I don't know, virtually infinite amount of points in the regime, in small neighborhoods of these points. And then, of course, that if that is your assumption that the neighborhoods of these points are also viable, but also belong to the same class, that sort of applies a regularity, smoothness condition in it. But you can have virtually infinite amounts of training data. Well, virtually, it's not actually going to enlarge your data set. Also, what you can use is to have some sort of stochasticity in your model. If you have been doing image classification, you know about dropout, when you randomly switch off certain neurons in your training data in your model, and make your network learn without using those neurons as well, etc. What we are going to do is this one, to penalize the parameter norm, because it works surprisingly well. And the reason it does is, well, the intuition behind this is that for the model to have really good, have really weird shapes, it's going to need larger parameters. If you constrain it to have smaller parameters, so the parameters should be around 0, then you will have a much better behaving, much more well-behaved model. So let's do that. And funnily enough, PyTorch already includes a nice facility for this. I'm going to actually copy the train code from here. Where is it? Ah, here it is. And the only thing that's needed, the only change that's needed, is that this optimizer has a parameter called weight decay. Yes, here it is. Can you see it? And the weight decay what it does is will constrain your parameters to be around the norm. So far, if you went at it from an optimization point of view, what you wanted to do is to have the minimum with respect to the, I don't know, W parameters. These are the parameters of the model, of your training loss. Let's say this is the training loss, which depends on the input, the output, and the parameters. And then this was before, and now you will have some sort of a extra term where you have the regularization parameter that only depends on W. And this whole thing, so your model is going to optimize this whole thing altogether. And what this does, well, in this case, the regularization term is going to be simply the norm of the vectors. If I remember correctly, either the norm or the squared norm. We have to look up the documentation for that. It doesn't really matter at this point. So this is basically the sum of from I. Sorry, let's write it like this: W1 squared plus W2 squared plus W, I don't know, K squared. Well, in this case, we only have 2, so. Sorry, no, not 2. In this large model case, we have K equals 10,000, yes, because these are not the input features, these are the parameters. And we are going to have, let's say, a weight decay. This is called weight decay, or L2 regularization, or I think Tikhonov regularization is also a name for it. And we are going to have, I don't know, some sort of a coefficient for it. Let's call it alpha. And this alpha coefficient is what this weight decay parameter is. So basically, the higher this is, the more constrained your neural network is. So for example, if I say that, let's run this cell. We train a regularized large model, which is the same larger model. And we train using the new regularized weight decay scheme. And if we change this weight decay to something ridiculously high, like 10, what you will have is, let's say, run it for, let's say run it for, okay, just for 200. You will have low accuracy because it takes only the second term into account, basically, and does not really take the training accuracy into account. Yes, so it did not really learn anything. Sorry about that. And the test accuracy, well, it's worse than the train accuracy. And what it did was, let's try to print out the model regularized large font parameters. So basically, this is the first parameter of the model. This went to 0, basically, because we told it that it really needs to minimize the magnitude of the parameters. Well, and it did. So this is sort of a hyperparameter. This is a trade-off again, so as not to. We can also underfit with this one as well. But this is some sort of. So this is a sort of a regularization from another direction than the small model side. So if you want it to do something difficult, but want to generalize it well, you need to use different methods of regularization and see which works best. Let's try to train it using a weight decay of 0.001, which I found offline, before the class, to work sort of well. And in the meantime, we have 1 minute, apparently, for you to ask questions, if you have any. Okay, no questions yet, and this is already run. Well, a couple of seconds. Okay, so what we can see here is that the model accuracy is better. The model accuracy on the train is worse, train data set, because remember, let's go back to this. Yes. So here, the simple large, and this is the same model, just different optimization algorithm. with some regularization. So with simply training the model and trying it to maximize the accuracy on the training data set, it was 93%. Now it's 85%, but it's 84% on the test data set, and it's the best out of all three or all four on the test data set. So regularization in this way, so it's even better than the simple model. Well, the simple model was only trained for 200, but you get what I'm saying. It can be better than the and the large model is also 93%, only because we sort of stopped it. It could have gone, I think, higher if we let it run more. And that thing in itself, that I stopped it early, that I determined that it should stop at 2,500 iterations or epochs. That also is a regularization. It's called early stopping. So this figure here, this double descent curve, it also works. So model capacity, you can exchange this, for example, with let's say number of epochs as well, because the more you train, the more capable your model will be. Basically, this is sort of like increasing the model capacity. It's not, yeah. So it's not increasing the actual capacity of the model class that you sample from, but it's well, it can be thought of that like that. So basically, one thing is to try to stop at the point where your test accuracy is going to go be small still. How you can do that is going to be, I think, yes, the topic after this one. But before that, I'm going to show you what the regularization did. So again, you can see here that you have this shape. It's more sophisticated than the simple one because you have a more powerful model, but it's not as, I don't know, weird. You don't have these weird holes. It doesn't try to fit every single outlier, every single sample point here. So it's sort of a better trade-off. So this is another tool that you have in your arsenal. This was just a sort of illustrative example. This class is not going to be comprehensive or exhaustive of the tools that the machine learning community has by any means. Not at least because these are always evolving. And they have the best practices are always evolving, not only the state of the art. So this, what I want to conclude and what I want your first take-home message to be is that yes, machine learning starts out as curve fitting, but after a while it stops being. It starts to become a little bit more, and then you have to start thinking about all the things that you don't know, basically all the data that you haven't seen yet. And that's generalization, and that's where you become a little bit more intelligent than a curve fitting algorithm. And one way is to do that is to do regularization. And of course, this sort of regularization, like constraining the stopping early or constraining the magnitude of the parameters, is sort of domain agnostic. You can have all sorts of domain specific regularization as well. The only thing that comes to mind off the top of my head is that, for example, in physics, you have all sorts of physical constraints. You can have all sorts of values and measures that cannot be zero. Cannot be negative, for example, and then you can constrain your model so that it doesn't really produce any negative values or stuff like that. I know it's a silly example, but you get my meaning. At this point, are there any questions? This is sort of, we only have one topic left. We might finish a little bit early, if that's all right with you.
Does this mean that in theory it's impossible to create a model which is like 100% good and always gives the correct assumptions?
In theory, it is possible. You just need infinite amount of data, training data. So what I haven't really talked about yet, or actually I haven't really talked about because it's a sort of hours ago, but as you get more data, this problem becomes even less of a problem. So one of the first breakthrough, so I think Andras has talked about this a little bit, but two breakthroughs were needed for deep learning to really shine. One is the GPUs and the accelerated hardware, and the second is the availability of, and third is the convolutional architecture. But the second was the availability of high amounts of data. So if you have high amounts of data, then your generalization is going to be much better. So if I generate, I don't know, lots and lots of data, I can try that if you want, by the way, because I can run the generating script, and let's say I am generating 500,000 data. Oops. I'm not sure how long this is going to take to run, by the way. And then reload it. And then let's say that I increase the batch size to something more. And then if I run the larger model, okay, it's a bit faster this time. It really needed the larger batch size. So if I have more data, the output should look more. It should look more better. And the other thing that I've mentioned is that if you have double descent, and this is a weird area, so I don't really know that much about it. If you want to learn about it, you should visit this website called inference.vc. This guy is a genius. Ferenc Huszár, he's a professor at Cambridge. His whole work and research interests are theory and how, well, not whole, but some one area he's interested in is how neural networks can learn better. So with neural networks, there is this weird generalization that's going on, and you can have really large models, huge amounts of data parameters, but also for ChatGPT to work, it needed a lot of compute and lots of data. It not only needed data, but it also used reinforcement learning, which was another. You can think of it as a regularization technique. But it also needed, I don't remember what the training dataset size of ChatGPT was, but I think it was also in the millions. And you can also, if you don't have the data, and it does seem that it tries to overfit, you can try to inject some features so you can resort to feature engineering. So for example, if you can transform, and back to your question, actually, if your data is noisy, it's of course theoretically impossible to have 100 accuracy. That is true. This is so-called, there is a limit, the so-called Bayesian error, if I recall correctly. It might have a different name. So the theoretical minimum error you can have, because if you have, so for example, if you have the same data point but with multiple labels, then you're going to definitely have some errors in your data set. Sorry, in your classification. And let's look at this is also a model accuracy. This ran back to 85%, but this wasn't a regularized model at all. So if you visualize this, It's going to take some time because it's going to try to plot every single data point on this plot. But this is going to look nicer. In the meanwhile, did that answer your question?
Yes, thank you.
Yeah, you're welcome. Any other questions? Or this was a good question, by the way. If there are no questions, I am going to, I might not, oh, here it is. So I'm not sure if you can see it, but your data point is so large, sorry, data set is so large that this is the fine line that the classifier, that the training algorithm learned by fitting on the data. This, well, looks more or less like an ellipse. Maybe if we gave it a little more epochs, then it may have converged to something more like an ellipse. But this is the best it can do right now, and this is not as weird as it was before. Because I can't be quite sure, because the separator is blue and the negative class is blue. So, but I don't think I can see any sort of, these islands that were present before. So with more data, it's less of a problem. But you always data at one point it's expensive, and if you want to have a competitive edge, it's even more expensive. Yeah. Okay, I'm going to close this. So I had question is that we have defined multiple model classes. We had this simple model, we had this polynomial model, we had this large model, and we had this large model with regularization. We could choose at which point we should stop the training, which is the number of epochs, and at which point how much weight decay we should get. There are also certain parameters like what initialization should we use, what sort of optimizer should we use, I don't know, what sort of how wide each layer should be in your neural network, and these are all sorts of hyperparameters. They're called hyperparameters because the parameters are the model weights, and the hyperparameters are the parameters of the training process. So the training process optimizes the parameters, and the hyperparameters control the training process. And we as engineers optimize the hyperparameters. Well, actually, there are some automated hyperparameter optimization tools which also have hyperparameters, but that's sort of out of the scope. So my question is, if we do this in a loop, so let's say something like train, evaluate, and then repeat. Well, either repeat or done. If it's still bad. And here comes the training data set. Here comes the testing data set. The problem is that after a while, your test data set is going to get used up, and you're going to get overfit. You're going to overfit your test data set, and this is actually a common occurrence. So what to do about it? Ideally, your test data set should only be used once after you have selected your model, because this is this whole loop is sort of a training, or sort of this loop is your hyperparameter. So this loop here, this is the hyperparameter optimization, which can also be thought of as a training from a generalization point of view. Optimization. And you shouldn't use your test data set for that, because that becomes a training data set for your hyperparameter optimization. And it stops being independent from, it can also get you too optimistic result. So what you can do instead is use the so-called validation data set, where the validation is, well, it's something between the testing and the training data set. So it's sort of like a second level validation data set. It's I always think about it because you can have multiple tiers of validation data sets. I always think about it like if you're an informatics guy or a hardware guy, it's like the cache hierarchy in the memories. So you have a training data set, which is used for parameter optimizing, a validation data set that's used for hyperparameter optimizing, and the test data set is only at the end when you, I don't know, showcase to your boss. When you see, I can recognize all the cats in the world. So what I want to do here, and I mentioned that one hyperparameter we can optimize for, this is a special one because we can optimize for during training, is when to stop. So instead of, well, actually, we're not going to do that, but what I'm going to show you, or we're going to do together, but at least I'm going to do it at my screen and you can follow, is to, after each training epoch, we will do a training run on the validation data set, and then have a look at that curve as well. So we can measure the loss on the validation data set as well. So we are somewhere here. Yes. So again, we are going to redefine our training, algorithm, and I'm going to copy it again. But now I am going to have two losses, train losses and validation losses. And I'm going to use the train loss for training loss, obviously. Train losses. And then the val losses, well, actually, let's start with val accuracy because we have a nice function for that already. Val accuracy. And after each epoch, here the training has, so training has already run. So I want to have the accuracy of my model of the validation data set. How do we get the validation data set? Well, PyTorch has this nice function where it can split torch utils data, yes, randomly split your training data set into two. And we are going to have a training data set, as in the de facto training data set where we're going to train on, and the validation data set. So we split the train data set into, let's say, 0.8 and 0.2 ratios. So 20% is reserved for validation. And again, I'm going to go back to the smaller data points because we might, oops, this is not what I wanted. Smaller data points, that was 500. Yes, reload, please. Yes, 500 data points, excellent. So 20% is reserved, yes, and the output will be the actual train data set and the validation data set. Okay, so we have a val data set, but the train data loader is defined on the train data set, yes, and we do the accuracy and we save the accuracy, and the val accuracy accuracy append the accuracy of the accuracy on the val data set. Okay. And then again, I'm going to copy one of the codes about. So this is going to be, again, the large model because it can overfit nicely. And then the regularized large model, yes. And this is going to be called the validated model, let's say. Oops. Okay, and we need the loss, train loss, loss. Okay, and we had this code, yes, about the training, the loss outputs. And no, not this code, sorry. The this code, yes. I'm too lazy at this point in the evening to just write code. I'm just copy pasting. Sorry about that. So we are going to have, this is the training loss, and we are going to have, and this is not going to be the training loss, this is going to be the val accuracy, because we don't calculate the training losses yet. Accuracy, validated model, train data set, yes, validated model, train data set, test data set, and val accuracy, and this is the train loss, label val accuracy, which is just the accuracy in the validation data set, and this is not correct true anymore. Okay, have we trained this? No, not yet. I could have written while I was talking. By the way, are there any questions about this? While it's training or even after that, I mean, we still have time. Okay, so because of the weight decay, it didn't really overfit. Let's try to decrease this weight decay to 0. And I'm curious as to what's going to happen. Small overfitting, okay. Might need to train a little bit more. So this is what it looked like. This was the test accuracy. And the fun thing is that it starts out as some sort of cyclic behavior, which I don't quite know why. Oh, I forgot to add actually include the legends here. So this is the validation accuracy, the orange curve, and this goes out here as well. It's valid. It's nice. Okay. Actually, is this on the training data set? Sorry, is this on the smaller training data set? Yes. Okay. Never mind. We might need a little bit more coaxing for it too. And in the meanwhile, actually, I'm going to give it 300 just to be extra diligent. And then in the meanwhile, I'm going to write a script that I write a function that calculates the validation loss of the model on the validation data set. I don't need any more, I think. No. So I need a validation data loader. Torch utils data loader. Val data set. Shuffle false. Batch size equals batch size. And then for X and Y in validation data loader, I am going to need a torch null graph here because I don't want it to calculate gradients. The y predicted logits, or logits, no logits, I think, is the model applied to x. Yeah, it doesn't want to overfit. Why? Why doesn't it want to overfit? Weird. Okay. Maybe if I never mind. And then the loss is going to be nn.functional dot binary cross entropy with logits, and the input is the y predicted logits, and the outputs are the targets are the y. And let's say the loss, sum equals 0, and then some loss is loss point item times x.shape. And then the mean loss is going to be some loss divided by the length of the data set, which we were given. Let's format this code. Okay. Have I left out anything? It's similar to accuracy, but we don't measure the accuracy, we measure the loss again. But we don't take gradients, don't do optimization stuff, do nothing about it. Okay. And now we will have all validation loss, which is going to be calculated here. Val accuracy and val losses dot append val loss model val dataset. And we also return the val losses. Okay, and we also plot the val losses. Okay, and we also val losses label is the validation loss. Okay. In the meantime, are there any questions? Oh, that one. Ah, no, nothing. Okay, no worries. Still have 5 seconds. I sort of feel like you know, in a teleshop where they say that you have 5 seconds to click on this button, otherwise the goods are going away and the discount is going away. You have 5 seconds to ask your question. Okay, so we have the validation loss, and funnily enough, it's smaller than the training loss. And the reason behind that is that the training loss is updated after, so the training loss is calculated after each mini batch, after which the validation loss is calculated at the epoch end. So basically what we do is mini batch gradient update loss calculation, training loss calculation, update training loss calculation, update training loss calculation, and then a validation loss in the whole data set. So basically there will be a couple, not that much, but a couple training loss calculations that are going to be superseded by subsequent updates. So that could happen with when you plot validation loss like this. And well, this is, I think, the demo effect where you can't show what you want to show, in that you don't really I can't really show that sometimes the validation loss curves up a little bit, and the validation accuracy curves down a little bit, and then you know that at this point you need to stop your training. Let's try to do the same with a smaller model. And then see if it behaves similarly. Okay, even less. Oh, but at least the training was nice and smooth. And yes, the validation accuracy at least was, as our validation loss was at least a little bit higher this time. And what you can see here is that the accuracy, which is the thing that you want to optimize, is not always constant. See, it's a sort of step function because there are all sort of, because you have in your validation data set, you have a small amount of, I think, 100. If 500, 20% of 500 is, I think, 100. So you have 100 samples. So really, you will have small jumps from here to there. I think 1% jumps because you can't misclassify half a point. You can only misclassify one sample or another sample. So the accuracy is going to be a sort of discrete value. So in this case, you might start to think that, okay, this was your, so this is the maximum where your accuracy was the maximum. So this might be the best model, but at this point, I'm not quite sure that this isn't some noise or some random artifact that we can exclude because this is not that much of a difference between the final value and the. So yeah, more or less that's what I wanted to show you. So again, the 3 takeaways is that 1, you can overfit. You need to think about how to generalize. 2, you have arsenals. You have tools in your arsenal about how to deal with overfitting. Basically, you need to Google the keyword regularization or ask ChatGPT about it. And 3, you can do model selection, and you can monitor your own overfitting via this test validation split, and you can do it real time in your training. You can plot your validation loss, and then you can analyze the actual training algorithm as you're training your model. So this is quite fun. Are there any questions? That's all I thought about. So I came up with for today. You still have 3 courses an hour, so I guess yeah. But if you have any questions, then feel free to ask or discuss.
What is the good indication that we need to stop the training of the model?
Good indication would be if you saw something like, so this is your, oh wow, I don't want that color. So if you have this is your loss, this is your epochs, and let's say this is your training loss, and this is your validation loss, let's say. So at this point, it starts to go upwards. I think this is a good indication to stop here. And what you usually do is, this is, by the way, called early stopping. And what you usually do is to, as you train, you save the model parameters after each epoch, and you keep only the best or the 5 best models. And excuse me. After you have determined that, and there are algorithmic ways for that. For example, in PyTorch Lightning, there is this object called early stopping and callback, which you can use for stopping the training early. Then you can reload that module, that model that have performed best, and you can use that. You don't necessarily need to use the last model after all the iterations. So you don't necessarily need to use this model. Oh, sorry, this model. You can use this model as well. And this is also good for if you don't have, so sometimes you say that, okay, I have this amount of time and this amount of compute. I want to run it on 100 epochs, or for 100 epochs. But sometimes you say that, okay, I leave it running for the night and let's let it stop itself when it thinks it's ready. So then again, monitoring, for example, the validation accuracy, validation loss, and if it starts, stops decreasing, you can have some sort of a patience. So for example, I usually have 10 or 20 epochs for which I just let it run. I mean, and not me. It's in the algorithm. It's the early stopping algorithm, where we wait for 10 epochs to start, to let's see if it starts going down again, or it was just a temporary bump in the training process, because it's this sort of all sort of noisy stochastic behavior. Does it answer your question?
Yes, thank you.
No worries. You're welcome. Any more questions? Okay, then, if you don't have any questions, then I'm going to leave you for it. Thank you for attending. Thank you for the nice questions, and have fun and enjoy the evening and the rest of the course. Bye.
Thank you. Bye.
Thank you. Goodbye.